So for this last video in Chapter 9, we're going to look at a couple more addition reactions of alkynes. So for this one, very similar to what we saw in Chapter 8 with this hydroboration oxidation, this anti-Markovnikov addition of OH. It's very similar to that last reaction we saw, where we have the enol forming, or this alkene alcohol, and it tautomerizes to the ketone. Okay, so the same exact thing is happening here, essentially. One caveat to this, though, is that this only works with internal alkynes, right? Not an alkyne at the end of a chain. So one thing we can do here to change up conditions a little bit is we can make an aldehyde from an alkyne by using a bulky boron group and external alkyne. So let's say we have this alkyne here, right, simple butane, and for our conditions, they're going to be pretty similar, but we're going to change up one thing. We're going to use something called 9BBN THF. And then for 2, we have our peroxide like usual and our NaOH. Right, so 9BBN, you don't need to know what this is. I'm not going to draw it out because it's kind of complex, but it's boron just like BH3, but it's bulky. So there's these big carbon groups here that are pretty massive. So it kind of changes the intermediate that's happening, which allows us to make this aldehyde instead. Right, on that last carbon, right, this anti-Markovnikov addition happening here, right? So we have 1, 2, 3, 4 carbons and 1, 2, 3, 4 carbons with the aldehyde off the end here. So for this last reaction is similar to the dihydroxylation we learned, right, adding on those 2 alcohols to the alkene, right, in that sort of syn addition. We're seeing similar conditions here using KMNO4, H2O, and then neutral conditions. And so to orchestrate this, what's happening is we're getting this intermediate first of this alkene with OHs here. And then what happens is, right, the alkene reacts again, adding on even more OHs. So now we have all these hydroxyl groups right next to each other, and this is pretty unstable. So what actually ends up happening is similar to what we saw with the tautomerization, where those electrons are going to come down and actually remove those OH groups. We don't need to know the mechanism for that, but that's essentially what's happening, right? Those OHs are kind of falling off in replacement for this diketone here. Right, so on this alkyne, instead we're seeing, at the end of this transformation, 2 ketones. Now this changes if we have harsher conditions. If we use KOH and heat instead of neutral conditions, we get the following, where the alkyne actually sort of splits in half. And so we see at the end here, instead of ketones, we actually see carboxylic acids. Again, making sure we're counting up our carbons appropriately. We want to make sure we have 5 here, or sorry, 6 here, as is our starting materials. Okay, so we either make a dicarboxylic acid or we make diketones, depending on if we use neutral or harsh conditions. And so for this very last reaction here, Spoilers, I guess. Ozonolysis, again, a similar reaction we saw in chapter 8, we get a ring opening. So once again, this alkyne is going to split in half with these conditions here, and we're going to get, again, 2 carboxylic acids. Okay, so it's basically identical to the last reaction we saw with potassium permanganate, except for this time we're not seeing a cycloalkyne, so we're seeing 2 variations split off here. So this actually cuts right in half to get us our 2 carboxylic acid groups here, right? And so this is all we kind of need to know. We don't need to know the mechanism for these reactions. If I need you to know the mechanism, I'll draw it out. But some of these are a little bit, kind of complex and sort of beyond the scope of what we need to know here. Okay, so these are all the reactions that we're going to look at for alkynes. Okay, and it was kind of a lot, right? There's kind of a lot going on here in terms of getting various products. So we'll get some practice putting these together. And one way we can practice, and we'll talk more about this in class directly, is doing retrosynthesis. We did a little bit of this in Orgo 1, I guess depending on who you took it with. But one thing we want to be able to do now is we're building up this sort of toolbox of reactions, right? And so one thing we want to be able to do is have a starting material, have a product, and come up with a way to get from a starting material to a product, okay? And there's a sort of a rule set here, or guidelines in terms of doing these retrosynthesis problems. And we'll discuss this more in class, particularly with this problem here. So you can go ahead and take a crack at it on your own if you want, but when we come to class, what we're going to do is we're going to look at how do we make this molecule here, right, it looks kind of complex, with these starting materials and any sort of reaction we've learned during class.